Hey everybody, this is lesson 6.3. In this lesson, we are going to cover the inborn errors of protein metabolism, protein requirements, and the consequences, the physiological consequences of either protein undernutrition or protein malnutrition and protein overnutrition. So to begin, we will talk about the inborn errors of metabolism. There are several that are described in chapter 6. I am going to go a little bit more in depth about 3 or 4 of these, but I'll give an overview of all of them. So first we are going to talk about phenylketonuria, or PKU. This condition is an inborn error of metabolism, of protein metabolism, and this is directly related to the phenylalanine hydroxylase gene, okay, and the gene that codes for phenylalanine hydroxylase. So the process that is disrupted in PKU is the conversion of phenylalanine to tyrosine. Okay, so naturally, our cells are able to convert the amino acid phenylalanine into tyrosine, and then tyrosine can be converted into acetoacetate, which can then be converted into acetate or acetyl-CoA. So like I said, with PKU, the conversion of phenylalanine to tyrosine is problematic, and that's because of the gene phenylalanine, the enzyme phenylalanine hydroxylase. So individuals with PKU do not have the gene that codes for phenylalanine hydroxylase, and so they cannot convert phenylalanine to tyrosine. So with PKU, phenylalanine will build up in the blood, and that can lead to irreversible brain damage, intellectual disabilities, behavior disturbances, and seizures. So this is one of those inborn errors of metabolism that are going to be evaluated at birth. Next, we have 2 conditions of inborn errors of metabolism related to tyrosine metabolism. We're going to talk about tyrosinemia type 2 and alkaptonuria. So naturally, tyrosine can be converted into acetyl-CoA. As you can see here, this is a process where we're starting with tyrosine, and eventually through a few different processes we can create acetyl-CoA. So with tyrosine metabolism, there are 2 different inborn errors of metabolism that we'll discuss. The first is tyrosinemia type 2. With tyrosinemia type 2, we have a malfunction in the enzyme in the gene that codes for the enzyme tyrosine aminotransferase. So remember when we talked about transaminase reactions and how some amino acids can be converted into other molecules? Those are likely going to use transferase or transaminase enzymes. And so tyrosine aminotransferase here is the issue, and without that we can't convert tyrosine to this intermediate form. So if we can't convert this, then tyrosine will build up in the blood, and that is why it's called tyrosinemia, and this is type 2 form. Okay, so if we can't convert tyrosine with tyrosine aminotransferase, we're going to have an excess of tyrosine in the blood. The second condition of tyrosine inborn error metabolisms is alkaptonuria. This is further down the line of this conversion from tyrosine to acetyl-CoA, and the enzyme that is causing this is homogentisate deoxygenase, which we see right here. Okay, and its job is to convert homogentisate into what is called malacetoacetate, which we see here. So the problem with alkaptonuria is that the gene that encodes for this homogentisate deoxygenase enzyme is malfunctioning, And so we are going to have a buildup of homogentisate. Okay, and this is what causes alkaptonuria. So I think it's important to note that these conditions, these inborn errors of metabolism, of course, cannot be fixed. The only way to treat them is to avoid the consumption of the amino acid that cannot be metabolized. So remember, we're talking about inborn errors of metabolism, and these are directly related to how the genes are coded. So these are genes that are defective, and because of that, they can't create the enzyme to metabolize these nutrients. And so we have to, with PKU, follow a low phenylalanine diet. And then with tyrosine, inborn errors of metabolism, we will have a low tyrosine diet. Next up are the inborn errors of metabolism related to maple syrup urine disease. These are affected by the metabolism of our branched chain amino acids, valine, leucine, and isoleucine. Okay, so the common enzyme that is defective in maple syrup urine disease is branched chain alpha keto acid dehydrogenase. Okay, so we'll see that here. The overall issue is that we don't have the correct enzyme to convert our branched chain amino acids, valine, isoleucine, and leucine, into these important coenzyme A derivatives, which we see here. We see succinyl-CoA, acetyl-CoA, aceto-acetyl-CoA, acetyl-CoA, and succinyl-CoA again. So with maple syrup urine disease, the gene is defective that codes for that branched chain alpha keto acid dehydrogenase enzyme, which we see here. And so this will lead to an accumulation of the branched chain amino acids in the blood. If we have that buildup of branched chain amino acids, what can happen is the feces and urine will smell like maple syrup. They'll smell sweet like maple syrup. And that's where the name maple syrup urine disease comes from. So it's not just this kind of funny symptom, but it can be very serious in that it can cause respiratory difficulties, coma, and death within 1 week. So again, this is another one of those genetic conditions that doctors will test for as soon as baby is born. I did also want to note that leucine is perhaps the most problematic of the branched chain amino acids in maple syrup urine disease. So while treatment includes diets low in these branched chain amino acids, leucine is probably the one that needs to be most regulated in the diet. Okay, next there is inborn errors of metabolism related to methionine metabolism. We have hypermethionemia, propionic acidemia, and methylmalonic acidemia. Okay, and these are all related to defects in enzymes that help to metabolize methionine. So if you remember, we've talked about methionine several times and how it is a methyl donor. But one of the other important pieces related to methionine metabolism is that methionine is a precursor to cysteine. Okay, so you see up here we have methionine, and then eventually, okay, we can convert methionine into cysteine. Okay, so with these inborn errors in metabolism related to methionine, of course our treatment is going to be to limit methionine consumption, but we may also have to supplement these individuals with cysteine because methionine is so important for creating cysteine. Okay, so this first inborn error of metabolism called hypermethionemia is related to something that we've also already talked about before, which is SAM. So we have talked about how methionine can be converted, methionine can be converted into SAM, or S-adenosylmethionine, and that is the form of methionine that really likes to offer that methyl group to other molecules. So a really important process, and the enzyme that allows this conversion of L-methionine to SAM is methionine adenosyl transferase. Okay, so here again we have another transferase enzyme. So this specific enzyme is encoded by a gene, and whenever there's a defect in that gene that encodes for methionine adenosyl transferase, that is what leads to hypermethionemia. So if we don't have the enzyme to transfer or convert methionine into SAM, we will have a buildup of methionine. Okay, so that means hypermethionemia, which means high methionine in the blood serum. Okay, so that's our first type of methionine inborn error metabolism. The other are propionic acidemia, which we see here at the bottom, and methylmalonic acidemia. So these two types of methionine inborn errors in metabolism occur further down the line of methionine metabolism, but these are more so related to the conversion of methionine to cysteine. And so this is where we would really need cysteine to likely be supplemented. Okay. All right. There are a few more inborn errors of metabolism. I'm not going to go as far into depth with these and show their metabolic pathways, but it's important for you to know the conditions, which amino acid they're related to, and the enzyme that they're related to. So with tryptophan metabolism, we have two inborn errors of metabolism. That can be alpha-ketoadipic aciduria. This is a defect in the alpha-ketoadipic dehydrogenase enzyme. And then there's glutaric aciduria type 1, which is caused by a defect in the glutaryl-CoA dehydrogenase enzyme. Then we have threonine inborn errors of metabolism. Again, we have propionic acidemia that could be due to a defect in propionyl-CoA carboxylase. And again, we have methylmalonic acidemia that results from a defect in the methylmalonyl-CoA mutase enzyme. So moving on to protein requirements, just to touch back on what we've talked about before, the balance of nitrogen, similar to the balance of energy, and how that is going to regulate body composition. Nitrogen balance is important for understanding protein anabolism versus protein catabolism. So here we're looking at the basic requirements for adults and protein consumption. This is showing you a little bit about how they came up with these conclusions, but generally the RDA that's recommended is 0.8 grams per kilogram of body weight per day of protein for normal healthy individuals. Some recommendations do go up to about 1.2 grams per kilogram, but for a normal healthy adult, about 0.8 to 1 grams per kilogram should be adequate in times of hypermetabolism, or if an individual is ill or recovering from any kind of condition. This is whenever we would go up to this higher protein allotment. Okay, so proteins are important because from a metabolic standpoint, because a lot of the molecules and substances that we've talked about so far this semester, such as carnitine, we'll talk a little bit more about creatine next semester, but many substances, also like epinephrine and norepinephrine, these are all derivatives of amino acids, meaning we need amino acids to be able to create these substances. So if we have inadequate protein consumption, it's not only going to affect our body composition, but it can also affect metabolism as a whole, especially if we are excluding essential amino acids, because these essential amino acids are most important for creating these specific substances. So again, let's take a look at are essential amino acids. The list, remember, histidine is sometimes considered essential and sometimes not considered essential. And we've talked about the limiting amino acids. The most common limiting amino acids are lysine, methionine, cysteine, threonine, and tryptophan. And that just shows you that these specific essential amino acids are very commonly utilized to synthesize other substances and molecules for the body. And finally, we are going to talk about protein and body composition. There is extensive research on the branched chain amino acids and how these affect body composition. Perhaps the most research specifically is on leucine and I should say supportive of leucine. So it's found that leucine specifically, when consumed in conjunction with a well-balanced diet that's adequate in energy and in protein, that leucine can help to increase lean body mass, decrease adiposity, so the amount of adipose tissue or fat stored, and decrease body weight in general. So to achieve these results, it's recommended to have 7 grams of leucine consumed per day to increase lean body mass in older adults. And it's also more about the distribution of leucine consumption throughout the day. So we don't want to have 7 grams of leucine consumed at one time, but rather about 2 to 3 grams of leucine in incremental meals. So beyond the basic body composition changes that can result from the branched chain amino acids, we also see changes at the cellular level when branched chain amino acids are consumed, and that is through the mTOR pathway, the sirtuin pathway, the AMPK pathway, and then the PGC1 alpha complex. So basically, these pathways tell the cells when to be upregulated, to grow, to develop, versus when they should kind of hang back and focus on cleaning up what's already happening. So we're looking at the difference between growth and development versus repairing and trying to live in within itself in the most efficient way. So whenever we consume branched chain amino acids, the cells actually can upregulate the mTOR pathway, the sirtuin, AMPK, and the PGC1 alpha complex. So when that happens, the sirtuin pathway can enhance DNA transcription. So we have to think, if we're enhancing DNA transcription, we're building more proteins are going to be able to be synthesized from that DNA. More cellular components are going to be able to synthesize from that DNA as well. When PGC1 alpha is upregulated, this is going to increase mitochondrial biogenesis. So that means we are giving the cells the key to be able to produce more energy more efficiently by creating more mitochondria. We also see the upregulation of the AMPK pathway, which enhances liver fatty acid oxidation. So instead of storing these fatty acids and the liver kind of becoming sluggish, the cells are able to utilize those fatty acids as energy more effectively. And then we see that the mTOR pathway helps to stimulate protein synthesis via branched chain amino acid consumption. So this is very much at the cellular level. If you pursue a master's degree, you may see a little bit more about these cellular pathways and how diet can impact them. It's pretty interesting. Okay, so whenever we have excess dietary protein consumption, there are a few concerns. This would be a very chronic, very high consumption of protein. With that, we can see increased renal stress, demineralization of the bones, perhaps an increased risk of colon cancers, and that's more so related to the types of protein that's being consumed, as well as obesity, because if we're eating more protein, we're likely consuming excess energy as well. Americans typically are consuming more protein than is recommended or required by the body. Usually it's not problematic, but there are some populations in which this could be an issue. So for people who already have some type of kidney deficiencies, bone composition issues, as well as an increased risk of cancers. On the other hand, we can have issues with a low protein consumption. Now, our body can adapt to low protein intake by minimizing how much of the amino acids that are present in the body are oxidized. So instead of using amino acids that are free in the body for energy, the body would use the amino acids for synthesizing whatever proteins are required whenever there's not enough protein being consumed. And we're also going to see that the action of those oxidative enzymes won't be as high to oxidize those amino acids. We're also going to see a decreased action of the enzymes in the urea cycle. That is kind of a given, because if we're not oxidizing as many amino acids, we're not going to have as much ammonia, and we're going to have a smaller need or lower demand for creating urea through the urea cycle. So, few conditions related to protein undernutrition are hypoalbuminemia, which we're going to see on the next slide, sarcopenia, as well as marasmus and kwashiorkor, which we see here. So marasmus and kwashiorkor can be commonly confused, which is why I wanted to show you these images. Marasmus is caused by a lack of total energy and protein. Okay, so we're not consuming enough energy and we're not consuming enough protein. What we see in children with marasmus is emaciation, skin lesions, this common face of agony, and poor immune function. Okay, so think back to the functions of protein, and it can make sense, especially with this poor immune function, why that would be a characterization. With kwashiorkor, we see a moon face, generalized edema, and potbelly. This is going to make a little bit more sense in the next slide, but this is a result of the cause of kwashiorkor, which is a lack of total protein or poor protein quality. So these individuals may in fact be consuming adequate energy or calories, but the issue is with inadequate protein in kwashiorkor. This is a video about hypoalbuminemia. I'm just going to upload this separately because I'm not sure if it's going to record as I record this lesson, but this is going to help you to better understand how low protein consumption is related to edema, and why we see that moon face, generalized edema, and fluid retention in the belly in kids with kwashiorkor, which you see here. So it's related to albumin, and we just have to remember that adequate protein consumption is required for the production of albumin. Okay, and last, with protein undernutrition, one of the considerations, especially in older adults, is sarcopenia and age-related sarcopenia. So this is the natural loss of muscle mass and muscular strength that we see in the older adult population. So this is perfectly normal, and this is something that this and the symptoms of kwashiorkor and marasmus are something that you would be able to pick up through the nutrition-focused physical exam as you're assessing for fat wasting and muscle wasting. But with sarcopenia, we have to be careful because it's almost normal in this population, although it can be detrimental to their health. So as we age, our muscles can atrophy, and with that, the muscle mass is going to diminish as well as our muscular strength. So it's important in this population that we encourage two things: adequate protein consumption, but also weight-bearing exercises. if we're consuming enough protein, but we're not working the muscle to continue to grow and be loaded, then our muscles are going to continue to atrophy. So we have to have the combination of adequate protein intake plus weight-bearing exercises. So the recommendations that I showed you earlier of 0.8 grams per kilogram of body weight to 1.2 grams of protein per kilogram of body weight are not enough to prevent the progression of age-related sarcopenia. And so in this population, probably about 1.2 to 1.6 grams per kilogram of body weight is more appropriate. And again, we just have to make sure that we are encouraging weight-bearing exercises in conjunction with this higher protein intake. So this is where physical therapy, occupational therapy, and weight-bearing exercises can really come into play to help maintain the health status of the older adult population.